Somewhere beneath a business district in southern China, a machine the size of a football field is making ice in the middle of the night. 4 floors underground, while the city sleeps, this machine quietly freezes enormous stores of water, then uses that ice the next day to cool an area of 19 million square meters. You read that number correctly, not one building, not one block, 19 million square meters, cooled without a single rooftop air conditioner in sight. Walk through this district in the daytime, when it's 95 degrees outside and the humidity soaks through your shirt in under 5 minutes, and every tower around you is silently, perfectly cold. Look up at the roofs, look along the walls, and you won't find a single condenser unit, no dripping window box, none of the usual machinery we associate with staying cool. That's because in this part of China, engineers didn't try to build a better air conditioner. They tried to remove it completely. And this is only the first stop on a much bigger story, because across the country, in an old airport turned into a new district, under a starfish-shaped terminal outside Beijing, in the wind, patterns of one of China's hottest cities, and even in ancient Ram, Earth homes built centuries ago, the same idea keeps reappearing. What if a city didn't need machines to survive the heat? What if the cooling was built into the land itself? You're standing in Qianhai, a shining economic zone on the western edge of Shenzhen, packed with skyscrapers, malls, subway stations, and data centers. It looks like any other modern skyline until you realize something is missing. There are no air conditioners. Not hidden ones, not cleverly disguised ones. For most of these buildings, they simply don't exist. What you can't see is happening underground, where Shenzhen has built one of the largest district cooling systems on the planet. 10 separate cooling stations connect through 90 kilometers of buried pipes, forming a network with a planned capacity of 400 refrigeration tons. That's enough to chill offices, shopping malls, train stations, and server farms spread across roughly 15 square kilometers. When a major regional newspaper described it as a giant air conditioner, that was technically true, in the same way a dam is technically a hose. The method behind it is refreshingly straightforward. At night, when electricity is cheap because demand across the grid is low, chillers freeze massive reserves of water and store that ice underground. During the day, as the sun bears down on southern China, that stored ice cools water to a low temperature, and this chilled water travels through dedicated pipelines into every connected building. Each building draws the cold out of the water, sends the water back warmer, and the entire loop starts again. If you've ever lived in a northern Chinese city where whole neighborhoods share a central heating system in winter, you already understand exactly how this works. It's the same concept, just flipped. Instead of burning fuel to heat water for a city, Qianhai uses inexpensive midnight electricity to chill water for a district. Someone looked at a heating network built for winter and asked what would happen if you ran it backward for summer instead, and nobody could think of a good reason not to try. The scale of the underground stations themselves is hard to picture until you're inside one. Cooling Station Number 5 sits 4 floors below ground, filled with an intricate maze of pipes, separators, and cooling units inside a hall large enough to hold a football field. It began operating in 2021, runs continuously through every day of the year, and on its own supplies cooling to more than 75 kilometers of public buildings. Remember, that's just one of 10 stations working together. Now consider what this actually costs and saves. Building the entire Qianhai system required an investment of roughly 4 billion yuan, close to 620 million US dollars. According to the company that operates it, once fully completed, the system is projected to save about 130 million kilowatt-hours of electricity every year compared to installing separate air conditioning units in each building. That's the equivalent of burning 16,000 tons of coal, and it cuts carbon dioxide emissions by roughly 130,000 tons annually from a single district within a single city. Part of this saving comes simply from consolidation. Centralizing all the cooling equipment reduces the total machinery needed by about 20%. Fewer machines mean less refrigerant circulating through the system, less maintenance, less clutter on rooftops, and none of that unpleasant experience of walking past a building's exhaust vent and getting blasted with hot air, as if the machine were personally annoyed at you. Shenzhen began planning this system back in 2014, after government researchers studied Shanghai's energy consumption and confirmed what people across southern China already suspected. Air conditioning was placing an enormous strain on the electrical grid. Rather than design a more efficient version of the same problem, Shenzhen's planners decided to remove the problem from individual buildings altogether. But Qinghai still has to manufacture its cold using electricity to freeze water into ice. About 30 kilometers away, another city looked at this same challenge and asked an even sharper question. Why generate cold at all when there's an entire ocean sitting right next door? That question leads us to Hong Kong, to a site that used to be one of the most famous runways in the world. This is the old Kai Tak Airport, the legendary strip of tarmac that jutted directly into the harbor, where pilots once threaded passenger planes between apartment towers so tightly that residents claimed they could see what was playing on the in-flight movie screens. That airport shut down in 1998, and when Hong Kong redeveloped its 320-hectare site into a brand new district, engineers buried something underneath it that most people who live and work there will never see or think about: the city's first district cooling system powered by seawater. To understand why Hong Kong needed this so urgently, consider one number. Buildings account for roughly 90% of Hong Kong's total electricity use. The global average sits closer to 40%. In a city this dense, this vertical, and this humid, air conditioning isn't just one expense among many. It effectively is the energy budget. So the government's Electrical and Mechanical Services Department, working alongside the engineering firm Arup over 2 decades of planning and construction, decided that the new Kai Tak district would not rely on thousands of individual machines each fighting the humidity block by block. Instead, the sea itself would do the cooling. The mechanism works like this. Seawater is drawn into central chiller plants, where it absorbs and carries away the heat produced during the chilling process, doing the same job that an entire forest of rooftop cooling towers would otherwise need to do. The chilled fresh water that results then flows through a massive underground network to around 50 buildings across the district: offices, hotels, schools, shopping centers, a children's hospital. The cruise terminal built on the old runway, and the new sports park with its 50,000-seat stadium. Each building draws off the cold it needs through its own substation, returns the warmed water back into the loop, and the cycle continues indefinitely, all while shoppers and commuters above have no idea it's happening. The engineering that makes this possible is remarkably intricate. The network is built as a ring circuit using a 3-pipe interlink system, with 2 pipes active at any time and 1 held in reserve, so a failure anywhere in the system doesn't shut down cooling for the whole district. Leak detection cables run alongside every steel pipe, so if water ever escapes anywhere in the network, operators back at the plant see the signal immediately and can isolate that exact section using remote control valves. The pipes themselves range from 1 to 1, 4 meters in diameter, and construction crews had to thread roughly 40 kilometers of them through one of the most congested urban sites on Earth, at one point digging directly beside a highway flyover that needed constant movement monitoring throughout construction. This isn't ordinary plumbing. It's closer to surgery performed on a city. The payoff matches the effort involved. Once fully completed, the Kai-Tak system will deliver about 462 megawatts of refrigeration capacity through roughly 63 kilometers of seawater and chilled water piping, serving around 2.5 million square meters of floor space. Even its earlier construction phase alone provided cooling equivalent to what 40 separate 30-story commercial towers would need on their own. The system consumes about 35% less electricity than conventional air-cooled air conditioning, and once it's fully operational, it's expected to save around 138 million kilowatt-hours of electricity every year, roughly the same amount consumed annually by 42,000 households. That's the power draw of an entire mid-sized town, saved simply by relocating the cooling process out of individual buildings and into the harbor. And here's the detail that ties this story together. Because the connected buildings no longer need their own cooling towers or condenser units, all of that heat-emitting machinery simply disappears from rooftops and streets. This means the district isn't only using less electricity, it has also stopped pumping hot air back into its own neighborhood. Every conventional air conditioner cools the inside of a room by heating the outside world. Kai-Tak breaks that cycle entirely, fighting the urban heat island effect just by existing. The ocean, in this case, becomes one giant heat sink, but China's most ambitious cooling project doesn't use the sea at all. It uses the entire planet. Fly into Beijing Daxing International Airport, the colossal terminal designed by Zaha Hadid that looks from above like a golden starfish caught mid-stretch. Land there, and you're touching down on top of the largest ground source heat pump array in the world. Underneath and around this airport, engineers sank 10 497 borehole heat exchangers into the earth, 10,000. Each one is a loop of pipe drilled deep into the ground, circulating fluid that exchanges heat directly with the soil surrounding it. The trick that makes the whole system work is almost embarrassingly simple. Just a few meters below the surface, the Earth's temperature barely shifts throughout the year, regardless of what's happening in the air above. So in winter, when Beijing freezes, the ground stays warmer than the air, and the system draws that warmth up into the terminal. In summer, when Beijing bakes, the ground stays cooler than the air, and the system pushes the building's excess heat back down into the earth. The planet becomes the airport's radiator in January and its heat sink in July, and the ground never sends an invoice for the service. 2 energy stations, running 8 heat pump units between them, serve nearly 2.5 million square meters of the airport. According to Chinese state media, the system extracts more than 560 gigajoules of shallow geothermal energy every year, saving the equivalent of over 21,000 tons of coal and cutting carbon emissions by more than 15,800 tons annually. One international assessment of the airport found that its ground-coupled cooling and heating system runs roughly 50% more efficiently than conventional systems, and researchers who studied the borehole field have called it the largest installation of its kind anywhere on Earth. The array is so vast that engineers deliberately rotate which sections of it are active at any given time, resting parts of the field so the surrounding ground doesn't gradually shift in temperature. After decades of continuous use, in the most literal sense, someone at that airport is managing the thermal health of the land itself, like a personal trainer for the earth beneath the runways. Daxing doesn't stop at the boreholes either. The entire site was designed from the start as one integrated passive cooling system. The terminal's double-layer metal roof works as high-performance insulation, keeping the summer sun's heat from soaking through into the building below. 47,000 square meters of skylights flood the interior with natural daylight, meaning the terminal isn't burning electricity on artificial lighting during the day. On a clear afternoon, the check-in hall and the fourth floor piers don't need their lights switched on at all. The glazing uses a specialized filtering glass that blocks about 60% of incoming heat, while still letting through 60% of natural sunlight. A balance that sounds almost too good to be real, but comes down to careful material science rather than any trick. And surrounding the terminal, a water management system captures and stores up to 8 million cubic meters of rainwater across constructed wetlands, lakes, and streams, a network the designers built specifically to prevent flooding and to soften the summer heat island effect on the surrounding area. Read that again. The airport's flood control system doubles as part of its cooling strategy. This is the pattern you'll keep noticing throughout the rest of this story. In China's newest infrastructure, cooling isn't something bolted onto a finished building. It's designed into the land before the first foundation is even poured. Which brings us to a massive city that decided to cool itself using something no factory anywhere can manufacture: the wind. Guangzhou is one of the hottest major cities in China, a dense subtropical metropolis of high-rises and highways where, between 1996 and 2014, urban temperatures climbed by as much as 1.5 degrees Celsius, with the worst of the heat concentrated precisely in the old, dense downtown neighborhoods where the largest number of people actually live. That's the harsh math of urban heat. It punishes density hardest, and Guangzhou has density in abundance. The city's response, developed in partnership with the World Bank, wasn't to install more cooling machines. It was to redesign the physical shape of the city so that nature could do the cooling instead. Guangzhou's planners began with an inventory cataloging every natural cooling asset the region already possessed: the mountains to the north, the Pearl River running through the center of the city, the surrounding forests and lakes, and the sea breeze rolling in from the south. They then mapped the region's prevailing wind patterns and carved out 6 major ventilation corridors running along those mountains and rivers, deliberately aligned with the direction of the wind. The central urban area alone is served by 5 major breezeways and 2 smaller ones. Picture it this way: a dense city full of tall towers behaves like a wall. Hot air gets trapped between buildings, exhaust heat from traffic and machinery accumulates, and the whole area turns into something like a convection oven with a subway system running through it. A ventilation corridor is a deliberate, permanent gap cut into that wall, a protected channel of parks, waterways, and height-restricted zones through which cooler air from the mountains and the coast can flow directly into the city's core and push the trapped heat back out the other side. The research behind this strategy is remarkably specific. Major corridors need to be more than 500 meters wide and angled within 30 degrees of the prevailing summer wind direction, or the air simply won't follow the path planners have drawn for it. Which means that somewhere in Guangzhou's planning offices, there are professionals whose entire job is essentially wind logistics, calculating angles and widths so that a breeze arriving from the coast actually reaches the buildings that need it most. The strategy climbs the buildings, too. Guangzhou has been rolling out vertical greening, plants grown directly on building facades, as a simple, low-cost insulation layer that lowers surface temperatures while filtering out glare and dust at the same time. Researchers modeling the city's airflow found something that validates the entire approach. The best ventilation corridors naturally follow existing vegetation and rivers, while automatically bypassing the high-density, high-rise clusters where heat tends to accumulate. In other words, the wind already knows the way through the city. The planner's real job is simply making sure nobody builds a 40-story tower directly in its path, protecting empty space on purpose in one of the most expensive stretches of real estate in the world. That might be the boldest decision in this entire story. No compressors, no refrigerant, no electricity bill, just a city planned precisely around airflow so that the wind itself becomes a piece of municipal infrastructure. But wind is only half of nature's cooling toolkit. The other half is water, and over the past decade, China has turned dozens of its cities into something that sounds almost invented: sponges. In 2013, Chinese President Xi Jinping declared that cities should function like sponges, absorbing, storing, filtering, and releasing rainwater using natural forces rather than fighting water with concrete. By 2015, 16 pilot cities had been selected, and the Sponge City program officially began. National targets followed soon after, 20% of urban areas meeting sponge standards by 2020 and 80% by 2030. The headline purpose of a sponge city is flood control, and in a country that regularly faces monsoons, gale summer rainfall, that alone would justify the entire program. But there's a second effect that most coverage overlooks entirely. The same infrastructure that absorbs floodwater also cools the city down. A conventional city is sealed under asphalt and concrete. Rain hits the surface, drains away within minutes, and the dry ground bakes under the sun for the rest of the week, absorbing heat all day and radiating it back out all night. A sponge city works in the opposite direction. It's built from rain gardens, green roofs, grass, lined channels, retention basins, restored wetlands, and permeable pavement that draws water down into the ground and holds it there. Much like an actual sponge, wet, vegetated surfaces cool themselves through evaporation, the same reason you shiver stepping out of a swimming pool on a hot day. The numbers here are striking. Research on these systems found that the surface temperature difference between impermeable and permeable pavement can reach up to 8 degrees Celsius, nearly 16 full degrees, achieved by changing nothing except what the ground beneath your feet is made of. And because permeable pavement holds onto water for days after rainfall, it continues quietly cooling the streetscape long after the storm itself has passed. Wuhan, a city built among rivers and lakes and one of the 16 original pilot cities, set targets for its sponge projects to absorb between 60 and 85% of annual rainfall while withstanding a 50-year storm event. Researchers studying Wuhan's thermal environment reached a conclusion that reads almost like poetry disguised as a planning report. Water is the city's single most effective cooling source, but scattered ponds are too small on their own to make a meaningful difference. The solution is to link smaller water bodies to the city's larger lakes through channels and wetland parks, creating a connected cold island effect across the entire urban landscape, essentially building a circulatory system for coolness. One economic analysis even found that Wuhan's sponge approach came in more than 4 billion yuan cheaper than a conventional concrete drainage alternative. Cooler and cheaper at the same time is a combination that almost never happens in infrastructure projects, and when it does happen, it tends to get built quickly. Now, before concluding that China has fully solved the problem of summer heat, it's worth pausing for an honest look at where these systems fall short, because there are real limitations here, and you deserve to see all of them clearly. The first and biggest limitation is this: district cooling mostly doesn't serve homes. The director of Qianhai's energy company put it plainly in an interview: residential buildings aren't well suited to district cooling because the economics depend on steady, predictable demand, the kind you get from offices, malls, subway stations, and data centers. An apartment where demand spikes at night and on weekends and disappears entirely when residents travel is a far messier customer for this kind of system. So the person sweating in a 6th-floor walk-up in July is still relying on a conventional wall unit, and China remains one of the largest air conditioner markets on the planet. These systems are shrinking the problem at the scale of entire districts. They have not erased it at the scale of individual households. The second limitation is just as important. District cooling really only makes financial sense under two specific conditions: a brand, new planned district, and a government with deep enough pockets to fund the upfront infrastructure. You cannot cheaply retrofit 90 kilometers of chilled water pipe underneath a century-old neighborhood already packed with existing foundations, subway tunnels, and utility lines. It's no coincidence that both Qianhai and Kai Tak were built on blank slates, a newly designated economic zone and a demolished airport. For the thousands of established, older districts across China and around the world, this particular tool mostly isn't available. Even the more advanced materials involved in this story come with fine print of their own. A study conducted in Shanghai found that applying a reflective roof coating cut a building's annual cooling electricity use by about 116 kilowatt-hours, but at the same time increased its winter heating demand by roughly 327 kilowatt-hours. A roof that reflects heat away in July also reflects it away in January, and in cities that experience cold winters that trade off can end up working against the building overall. Researchers refer to this as the heating energy penalty, and it's exactly why newer research is now focused on developing temperature adaptive coatings that change their behavior depending on season. None of this undermines the overall story. It simply confirms that what's being described here is engineering, not magic. A set of genuinely powerful tools that still have real edges and real limits. And honestly, the most impressive chapter in this entire story isn't modern at all. China has been cooling buildings without air conditioners for centuries, and today's planners didn't invent this playbook so much as rediscover it. Travel to Fujian province and step inside a chalu, one of the massive circular fortress homes built by the Hakka people sometime between the 12th and 20th centuries. The rammed earth walls are about 1.5 meters thick, built from local red clay bonded with lime mortar, and at the most critical structural joints, traditional builders reinforced mixture with brown sugar and glutinous rice paste. These buildings are, quite literally, ancient engineering marvels that are also technically a dessert. Those enormous earthen walls create what engineers call thermal lag. They absorb the day's heat so slowly that the interior stays comfortably mild through Fujian's long, brutally humid summers, then release that stored warmth back out overnight. The walls even breathe in a cyclical rhythm, absorbing and releasing moisture like a giant clay lung. When researchers actually measured the results, rooms inside these fortresses delivered better thermal comfort and stability than nearby modern concrete apartment buildings. An 800-year-old Ricean-forced fortress wall outperformed a modern concrete structure standing right next to it. Let that sit for a moment. Now travel northwest to Turpan in Xinjiang, one of the hottest and driest places in China, where summer air temperatures push past 38 degrees Celsius and annual rainfall barely registers at all. Here you'll find the Kerez, an underground network of gravity-fed water channels dug by hand over centuries, recognized in 2024 as a World Heritage irrigation structure and described as the largest underground irrigation system on Earth. Locals sometimes call it the Great Wall of Groundwater. By running water beneath the desert instead of across its surface, the Kerez cuts evaporation down to almost nothing, using no pumps and no electricity, just slope and patience. Traditional homes in Turpan paired this cool, flowing groundwater with semi-underground living spaces, where measured wall surfaces run around 8 degrees Celsius cooler than identical rooms built at ground level. Across the region's plateaus, cave dwellings use the surrounding earth itself as thermal mass, while in the humid south, skywell courtyards pull hot air upward and out of homes, using evaporative cooling to chill the rooms below, all of it centuries before anyone had coined the term air conditioning. Guangzhou's modern planners have explicitly cited restoring this kind of ancient architectural wisdom as part of their own current cooling strategy. In many ways, the ancestors already knew the answer,
Modern engineers simply spent 100 years plugging things into the wall instead of listening. Which brings us to the frontier, the technologies that could shape the next generation of Chinese cities that stay cold by default. Start with the simplest weapon imaginable, white paint. Measurements taken on an office building in Chongqing in 2012 found that a reflective white roof coating lowered the roof's surface temperature by about 20 degrees Celsius and cut daily air conditioning energy use by roughly 9%. Field tests of newer radiative cooling coatings have pushed even further, showing roof surface temperature reductions of up to 40% compared to bare aluminum roofing. One newly developed high-reflectivity evaporative roof coating, a reflective layer built over a porous, water-holding surface, lowered indoor air temperatures by about 2-3 degrees and cut summer air conditioning energy used by nearly 25% in testing, a quarter of a building's cooling bill, eliminated simply by what the roof is wearing. Then the story gets genuinely strange. Chinese researchers recently unveiled a type of cement engineered at the microstructural level to reflect 96.2% of incoming sunlight while simultaneously radiating its own accumulated heat away with 96% emissivity in the long-wave infrared spectrum, wavelengths that pass straight through the atmosphere and release that heat directly into outer space. It's a structural building material that also functions as its own cooling system. The wall becomes the air conditioner, the sidewalk becomes the air conditioner, and the heat's final destination is the cold void of space itself, which, as far as anyone has determined, does not charge by the kilowatt hour. So step back and take in the whole picture at once. Ice forged at midnight beneath Shenzhen, seawater looping silently under Hong Kong. 10,000 boreholes breathing beneath Beijing's newest airport. Wind corridors carved through Guangzhou by planners guarding empty space like treasure. Sponge cities drinking in the rain across Wuhan. Sticky, rice fortress walls that were beating the heat centuries before air conditioning was ever imagined. And now, cement that exhales its own warmth into deep space. The rest of the world is still asking how to build a more efficient air conditioner. China is increasingly asking a completely different question. What if the city itself was the air conditioner? And while everyone else keeps debating the answer, China is already pouring it into the ground, one district, one corridor, one sponge at a time.